Boom. Hello and welcome back to part 2 of related rates. The network. All right. So, we talked about related rates for the ice cube. Let's talk about oil spill. So what am I going to have here? I'm going to have an oil rig, and this oil rig is going to leak oil everywhere. So the oil would spread in circles, right, evenly out to all sides, ideally. Well, I mean, ideally is no spill. That's ideally, but if there is a spill, we can for ease of calculations. And as the time goes, this circle will grow. And we want to know how fast is the area of the whole thing over here. How fast is the area growing? Because you have to clean it up, right? Now the good thing is that oil only stays on surface, so you can scoop it up, right? It doesn't go everywhere. So that's the good part, right? So we can talk about the two-dimensional problem, just worrying about a circle. So what do I have? I have a circle, and if I have circle, then the area of the circle is very good. All right, pi r squared. So if I want to compute the change in area in time, well, I should take the derivative of pi r squared in time, because that is going to give me related rates with the change of area and the change of radius. Radius you can measure, right? Change in radius you can measure, because you look at it, right? You stretch a ruler on the sea, on top of the sea, right? The derivative of A is 1, followed by the chain rule dA dt. On the other side, you have 2 pi r as a derivative, and then dr dt as a chain rule, because r and t are not the same variable, so chain rule kicks in. And there you have it. This formula is related rates, which relates the change of area in time, and this one over here, change of radius in time. So these are the things that that we have. So now, if you look at the numbers, you just plug numbers in. So it's important for you to get the concept, get the geometry, and derive the equation. The rest is just plugging numbers in and getting 7 as the answer, whatever it is. So what do they have over here? They said that the oil spreads in a circular patch and all of that kind of stuff. The rate of 30 meters per hour. So 30 meters per hour. And the radius is 100 meters. When r is equal to 100 meters. So what you do is you plug all of these things in. So change in surface area, change in area, right, for the oil spill will be 2 pi times 100 for the radius times 30 for the change. Now observe that in this particular example, 30 is positive because the oil spill grows in time. It becomes bigger with time. So you want to mobilize and clean it up as soon as possible. The longer you wait, the larger area you have to clean up. And it grows in all sides, right? That's one of the things that also people don't understand. It's not a linear growth. It's a quadratic growth. Right? The same reason why you can't have, you know, the giant monsters like Godzilla. It's not physically possible to have something like that. Because when you have the size, linear size, you have to understand that it's a three-dimensional creature whose weight is going to go cube of a size. So if you go, let's say, 2 feet by a factor of 2 in height, you are going to have factor of 8 on weight, because 2 cubed is 8. So the oil, going back to the oil spill over here, as your radius grows 30 meters per hour, look what happens with the area. 30 times 100 times 2 is 6,000 pi. So you are, it's a 6,000 pi, that's 18,000, right? Pi is 3, all right? 3.14, but who cares? So pi is 3. So that's 18,000 meters squared per hour. So every hour you delay, I can't write h. Let me try one more time. There we go. Perfect. Now, this is actually very scary, because if you truly understand this concept, this is not 18,000 per hour forever. That accelerates as well, because when you wait longer, your radius became larger. So if the change in radius is 30 meters per hour, then this number of 100 increases all the time, which increases this further. Now that makes sense, because if you take a look at this circle here, right, this could be at t equals 1 hour. Look at that, t equals 2 hours. By the entire circle, you can probably fit this a little bit there. And then you have all the rest, right? So this change is crazy large, right? And it's accelerating at all times. So what we did over here is we did a snapshot in time, where I just say, all right, mobilize your forces quickly, because at this point we are rising at this speed. But that also accelerates, as I said, because if this is your 100 meters radius, well, this might be 120. Now put 120 here and see what happens with this number, right? So it is not you calculated the rate of change and now you can do, no, this is just a snapshot in time. You are going to have a different calculation for every time when the radius increases, and the radius does increase, right? Because we have 30 meters per hour. So, yeah, a grim example, but it's there, right? Time for cartoons? I guess so, right? Yeah, my houses still look like this, okay? I know they shouldn't, but they do. All right. That's you with a hat and a scarf. Happy. All right. That's you. This over here, however, it's an evil bully. It's a little snowball right here. Kicks it off. So what happens in the cartoon? Yeah. All right, fine. You're definitely not going to survive this. Should have started off with a smaller snowball. Don't buy a house where you have a situation like this. All right? Move to the city. Anyway, so you understand the idea. You put a little spherical snowball, hence sphere, right, ball, and you kick it off the hill. Well, no, the person kicks it off the hill. You're on the other end, dying. It snowballs, right, into this menace. What is happening with the volume of this ball? In time, thank you. Just say grows in time, expands in time, right? It's getting larger in time. Great. So it picks up the volume, right? So what is the volume that you? What's the volume for the sphere? Yeah. Let's go. Where's the middle school now? Remember how you had that in class at one point in time? For something. Very good. That's exactly what it is. It's for something. All right. So now we're going to take the time derivative of this. d dt. Well, you got further than anyone else, so yeah. It has to have a pi too, right? So we can. So 4/3 pi r cubed. Volume. Oh, you didn't know this one? Oh, wait, the cone and cylinder and all of these things are coming up. Stay tuned. Yeah. So volume. Now what are we going to do? We are going to take the time derivative in this case. So volume is equal to 4/3 pi r cubed. Take the time derivative. So d dt. Implicit differentiation kicks in again. The derivative of a v is 1, followed with the chain dv dt equals, on the other side, 4 pi thirds is a constant. The derivative of r cubed is 3r squared, followed with the dr dt chain rule. 3's die. And we have dv dt equals 4 pi r squared dr dt. So this equation over here is your related rates. We can measure the size of the snowball and how much bigger it gets in time, because those are the observations that we can make, right? Let's say if you're looking at the snowball that it's already rolling at some point, right, when the radius is, let's say, 2 feet for the snowball, that's actually already 4 feet tall with a 2 feet snowball radius, right? Radius plus radius on the other end. If the radius is 2, then you have another 2 on this side, so it's 4 feet tall. Scary, right? But you are going to have r equals some number over here, and the r dt, oh, that looks like infinity. So let's pick like 1 feet, and it's picking up 0.7 feet cubed per second. Yeah. So we can calculate the change in volume as 4 pi 1 squared and then 0.7 over here. And we see how much volume-wise is added at that instant, right? So that's going to be 2.8 times pi. Let's call it 9 feet cubed per second. Can I call that 9? 2.8 times pi? 8.8? I'm going to call it 9. Because you're doing these calculations last second. It's crucial. Right? So this is it. Now they also have another example of the inflating spherical balloon, you know, or like the weather balloon. I don't particularly like those because it freaks people out. Aliens are coming. No, they're not. They have nothing to do here. Why would they ever visit this pathetic planet? To watch the soap operas on TV? The Bachelor? Travel across the galaxy to see nothing over here. Misery and death. And we don't even have fusion. This is how pathetic we are as a species. Please, they will be like they can't wait. They go across the galaxy to land over here to take our oil, and it's like, you know what that is? It's dead plants and animals. This is how pathetic we are as a species. You are refining dead plants and elements and animals, and you're exploding them in the engine on a 27% efficiency to go from point A to point B. That's how sad we are as a species.
Makes a pretty good sound, no?
Makes a good sound? Yeah. So when you sizzle something on the stove.
Sure.
Right? Try that one. So yeah. No. Any argument that aliens are going to visit here, just think of that one. There is nothing that we can offer. There is nothing for them to take. That's where we are as a species. It's just nothing, wasteland for them. Hmm? It would be like us observing an ant colony, where we might not be as sophisticated, actually.
People do that.
Yeah, they make little ant colonies. Yeah.
They just somehow figured out space travel, but everything else is
Like Autobots? I see your argument.
Superman, everything else is gone.
Oh yeah, the Superman, see? Yeah.
Pretty appreciative of Earth.
All of those premises are bad because in order for civilization to rise up to that level, these petty differences that we have and that we worry about, those would be solved far long in the past if the civilization is going to reach that level. If you think about the immense amount of resources that we are wasting on security and differences and fueling those, instead of pulling that money into education and science, just imagine how much United Nations does for the world and then realize that their budget is quarter of what police has in New York alone. So United Nations budget is a 1/4 of the budget of what New York PD has. And then think where is NSA and where is FBI and where is CIA, and think that we were as a species at the level where we don't need any of those. It's all taxes, all right? And I didn't even mention the military. Imagine none of that for any nation, because there are no nations, dream of mine, no nations. So think about that. On the planet, you have nothing. There is a little security thing in a space to prevent us from being wiped off by a rock. That's all you need. And the rest, the fusion and Dyson spheres and science and things, yeah. But now, waste of resources, because we are pathetic species yet. Still pathetic species. Anyway, let's see. Ooh, here's a cool one. Here's an airport. Here's a non-United Airlines airplane, which means this one actually has passengers and right. And here's another one right there. There they are. Getting towards the airport, and you know what? There's a separation between them. There's the distance d between them. Would you agree when this airplane is here and this airplane is here that this d is smaller? So as the distance from the airport for each one of these planes decreases, the distance between the airplane decreases. Can they land at the same time? No, right? So we have to have a air traffic control worry about those kind of things, right? So these planes are going to be moving. It's math. This is x-axis. This is y-axis, right? So we should have that in our minds. And you see, let's call it the X airplane. The X airplane is moving towards the airport, and if you carefully look at this, this airplane has a change of distance in time, right? Because the distance, x, will be changing in time, and this is its speed. Yeah, welcome to calculus, right? It all makes sense now. So you are covering the x distance from the airport in time, and that's your speed. And the other one is doing the same thing. It's just dy dt. This one is covering the y distance in time. And now those, if you are traveling on the airplane, they have the little TVs. You can, push the button and come to the screen, which tells you how fast you're moving relative to the ground. So when you consider these two things, you can calculate how fast is the distance between the two airplanes decreasing. And then you also know which one is going to arrive first, which one is going to arrive second, but you also have to worry about which plane has more fuel and things like that, because one plane could be closer with more fuel and the other one running on fumes, right? The other one is actually going to wait and give the advantage to the one with less fuel. So these are the things that computers have to figure out. Is it a human that does this? Is it? There are people there. Is it a human that does this? Oh, come on. Checking it? I hope not. I really hope not.
Our system tells the human if there's anything wrong, and then the human relays that to the clone. Oh, wow.
I hope no humans. I really hope. You're going to see now the calculation between two planes. This is just the United States. I mean, it's far busier in Europe, where the flights are $25 per flight. This is I know. So yeah, I hope there are no humans working. This is your computer science. Anyone? I need the code that's going to work, okay, 100% of the time. And then you zoom into any airport with hundreds of flights arriving and departing, and all of this has to have its. This is live. All of this is live, so you can follow. It doesn't really matter. I'm looking for United flight, but I guess none of these are. I know, right? So, yeah, it's really cool. Anyway, so I hope human element over here is at its minimum, like almost non-existent, because you have to deal with this. So now let's take a look at two-plane problem, where you have two airplanes approaching the airport. And oh, by the way, before I do this, you know what I found out? It's cheaper to have an airplane than a car. It's a little bit more expensive to buy it, but apparently at the local airports, you pay like $70 a month to store your plane on the airport. And then when you go out, some airports are charging $7 a day. So let's say you take your private airplane to, I don't know, Camp Maine or Chicago or whatever, and you land there, it's $7 a day to leave your plane parked at that airport. I can't park anywhere for $7 an hour if I take my car. And you go in your plane, and to rent the plane, it's I think like $130 per hour or something. Yeah, go figure that one out. Look up those prices. I was blown away. One of the flight instructors told me all these things. I thought, owning a plane is actually cheaper than having a BMW or Mercedes or some of the cars. Like, nice. All right. So finally, two airplanes are approaching the airport, and I want to see the change in distance between them. Well, change in distance better be dd dt, right? It's change in distance in time. So, great. What kind of geometry do I have? What do you see over there? A triangle, thank you. What type of a triangle? Right triangle. What are the formulas that we know for right triangle? Very good. Trig. Is trig going to be relevant in this particular example? Yes or no? No. Why? No angles, right? So trig is going to be right triangle and angles. We do not worry about angles here, so okay, great. What other things we know about the triangle? Pythagorean theorem. So see, it's a finite bag of formulas. You have area, not relevant. Perimeter could be relevant, right? Because it's one of the sides. Pythagorean theorem, which is what we are going to use because it deals with lengths of the side, and you have the d length, y length, x length. So that's the one. And then you have 6 trig functions, but no angles. So yeah, don't worry about the trig in this case. We are going to do trig eventually. So when I eliminate all of those, I get the Pythagorean theorem. Pythagorean theorem says x squared plus y squared is equal to d squared. And at this point, you have all of these things. Let's take the time derivative, see what happens. Sometimes you have to play with these things to, get somewhere. Oh, like everything else in life. Derivative of x squared is 2x. dx dt, chain rule, you have to have it. Plus 2y dy dt. Again, chain rule, you have to have it. And then distance, 2d, dd dt. 2's will drop. And what you see is that your dd dt is equal to 1 over d of x dx dt plus y dy dt. And this is your equation. So now you want to decipher this equation. Well, we can do that. It's not a problem at all. Dy dt, speed of the, call it the y plane. Y, distance of y plane from the airport. That's also something that it's known because we can measure distances. You know how far you are. Dx dt, speed of the x-plane. And x is the distance of the x-plane from the airport. And then dd is the current separation of the planes. Now this is the reason why I said hopefully no humans. You don't get to compute this every second of every right, every moment of every second, because all these things adjust as the airplanes are approaching. A wind could kick in, right, and then delay one of the planes slightly. Your calculations you did on the paper now have to be redone like this quickly, right? Human error, calculator. Where's my calculator? Batteries died. It's a lot of things. Pick up an Apple phone. You just don't have enough options. So these are, you know, there are a lot of issues you might have as a person there. And that's only 2 pi interaction. You've seen the zoom. It's still going. I mean, this is 24/7. This was not a snapshot in time, and now they're all landed. No. The airplane lands 3 hours, refuel, 2 hours, refuel, swap the people, swap the parts, right back up. See. When the same plane is delayed, they're changing an engine, okay? That's what they're doing if it's delayed. So, this related rates problem had, again, another 2D example of using geometry, and this time around, Pythagorean Theorem was the one. And you want to think about this a little bit because you have the you have a lot of formulas as options, right? The volume, the perimeter, Pythagorean theorem, and then 6 trigonometric functions. So you're looking through this maze of 9 formulas, and then one of those is the one that solves the problem. Again, you should be looking into the triangle and say, okay, it's a right triangle, I can do all the trick, but do I have a need for angles? Right? And if the area is not mentioned, most likely you don't need it. So the distances are dealt with Pythagorean theorem. So you should be able to figure it out. So we had some volume problems, said some. Let's do another issue. The launch for SpaceX finally had the good video coverage, all right, without, you know, Joe standing somewhere with the, you know, recording it. I guess they eventually figured out on how to do this properly. So let's do the space launch. Right? The book is launching a balloon, but you can't get to Mars in a balloon, so I'm not gonna do that. All right. Let's do the launch of a rocket. My rocket is going to look like a missile, because that's the only thing I can draw, somewhat decent. Okay, it's a missile, but it's a rocket. It's going to the Mars. Okay, this is where the people sit. All right, it's a rocket, and put some windows there. Enough. So we're going to launch this. It's going to go forward, up. Actually, it's going to go up, and over here we're going to have a camera. Best way to draw a camera, obviously, put a triangle at the end. None of them have it. But. Now the camera has an angle at which it shoots. It has a hinge over here. It's going to rotate with the omega. It's angular velocity. Hello, physics. What's my goal? My goal is to design a system, automated system, that it's going to adjust the angle of the camera, right, around the fixed point. As the rocket goes up, the angle is going right, what camera is recording is going to move automatically so that the rocket is in the center of the shot at all times. And then I don't have to have a human element shaking there, right, watching the whole thing. So how do we achieve this? Well, let's think about it. First off, we are starting at the camera looking at this rocket horizontally, and then the camera is going to rotate the angle theta to keep the rocket in the center of the shot as the rocket is going up. My question is, this is where your computer science kicks in, right? With mechanical engineering and electrical engineering and everything else. Computer science. I need a code. I need a code that will be able to update according to the equations that we come up with. And that code will be sending the signals to the motor, which is the motor that will adjust of how fast the camera will rotate up to keep the rocket shot in the middle. So what can I do, right? How do I design this system? Well, first off, you have to start with mathematics. Everything starts with that because you need a formula. If you have a computer code, it's expecting you to plug in mathematical formula. So you have to start there. All right, let's talk. You ask, what is the safe distance for the camera away from the rocket so that when the launch happens, camera is not melted, or the blast from all the fumes and the cloud is not covering right the camera shot. So what's the safest distance? They say, okay, 500 feet. I don't care, whatever, 1,000 feet. Put whatever is necessary, right? That's the first part. How far out was the shortest distance, right, for the camera? So once you have that, the rest you don't need. You have everything else. You have the geometry, and you have the distance, right? So we'll see what else we need, but again, that stuff is also readily known and available. So what we're going to do? Well, you're looking at this thing, and clearly you need mathematical formula. Now, which mathematical formula? First of all, what kind of geometry do you have? right triangle. Good. It's right here. Right. That's what a 90 degrees is. So we have a right triangle. Now we have a right triangle there. What is happening with the formulas? What formula we're going to use? Is area a good one? No, right? So, observing that we have the height over here and we have a 500 over here, what would be the good formula to use? Pythagorean Theorem? Do we need the length of this side? No. See, that kicks out Pythagorean Theorem. We don't need this side at all, so that kicks the perimeter as well. We agreed the area is not the one, so what's left? Trigs, good. Now, which one of the 6 are trigs? Tangent, very good. It's opposite over adjacent. Tangent theta is opposite over adjacent. In this case, tangent theta is equal to h over 500. So we have that as an equation. Great. So I have tangent. Now look what I need. I need omega. I need how fast do we get to spin the motor. Right? These motors are they're controllers that make motors move faster or slower. Right? So what do? Well, take the time derivative. Tangent theta is equal to h. You know what? I'm going to put a 500. So let me make h equals 500 tangent theta, just to make it nicer. And then take the time derivative of that. Mathematics will tell me what else I have to ask over there, right? What other things I need. So d dt. Great. Derivative of h is 1, followed by the chain rule dh dt equals to copy 500. Fine. What's the derivative of tangent? Secant squared theta. And then we also have to follow with the d theta dt. It's a chain rule, right? This is not t. And because it's not t, we have to follow with the chain rule. So d theta dt. Ooh, this is cool. Let's see what we have. What's this? What is this? What is this? Great. Change of height over time. What is it? The change of the altitude in time, which is speed of the rocket, right? It's covering the altitude, as you said, right? It's gaining the altitude in time. That's miles per hour, right? Look at the unit. Height is in miles. This is in hours. Miles per hour. What is it? It's the speed of the rocket. Great. Okay, so I'll definitely need to ask people to give me that one, right? So speed of the rocket. And what is this one? Change of an angle in time. Yeah, this is how fast it rotates. That's your omega. So that's the rotation of the camera, right? In adjusting the angle. Those of you, if I say physically challenged, then that's not actually what I want to say. Those of you challenged in physics, challenged by physics, challenged. Those of you who have no clue what the hell is going on in physics, there we go. Without trying to be nice about it, because I shouldn't. You know, physics, basic thing. What do you have? you have distance, velocity, acceleration for linear motion, right? So that's the linear side. And now you have the circular side, which is theta, omega, and alpha. Same concepts, same formulas given in, so that's the rotational motion, right? So you can move in a straight line, and that's your, right? So when you drive the car, but then when you go into a curve, this takes over, right? So now, the angular velocity, I don't know why I'm not using the proper words. Angular velocity. Of what? Of camera. That's the piece you want. Therefore, you better solve for it, because d theta dt is the one that you will be programming into. So what is that? Well, that's dh dt divided by 500 secant squared theta. Oh, great. There's more mathematics to be done. So the d theta dt, which is your omega, is equal to 1 over 500 times dh dt times the cosine squared theta, because 1 over secant is cosine. Yay! Great. So as you are programming, right, coding, you have to provide continuous input of speed of the rocket and the current angle of the camera. That will compute how fast you have to rotate the camera, or software rotates the camera, which are the impulses, electrical impulses sent to the motor, and the motor evolves in time. So now, do we have this info? Sure, you're starting with cosine of an angle, right, at 0, right, because it's horizontal camera, at 0, looking at the rocket. Well, cosine of 0 is 1, so we're all good there. And then the angle will increase, and keep adjusting as the speed kicks in, right? The speed kicks in, the angle changes, then feeds, and it's a loop, and it just goes from there. So I'm looking for the, there we go, SpaceX thingy, go right here. And I know we watched this, so we're not going to watch it now from scratch. I just want to point out the piece of information which we need, right? In our equation, we have speed of the rocket. Right? It's something that you keep track of at all times, right? So as you code these things, you have to have a continuous input coming from the various places. So you have to link your thing. Once you have the equation, which is what we have over here, this problem is solved. This is the solution for the problem. Sure, on the exam I will tell you when the speed of the rocket is 7 and the angle is 12, and you just plug those in and punch your calculator to get a number. But if you are able to get to this point, the next step is just to plug in 2 or 3 numbers and get the value on the other end. So, right? Critical thinking is important. We have a discussion on formulas, and then we have one more problem to do, and the section is over. I hope you're not disappointed, but that's what it is. You're expected to know every single volume formula, every single area formula, every single perimeter formula, Pythagorean Theorem, all 6 trig functions. Welcome to Calculus 1. Right, now, What was the formula for volume of the sphere? It was 4 something, right? So let's talk about the categories of all volume that you can get ever. Categorize them in 3 groups. 1, 2, and 3. So in the group 1, we are going to have your cube, your box, like the box we are sitting in, which has rectangles. The cylinder is going to be in that as well. So all of these shapes that look like this. The volume for all of these shapes is base times their height. B being area of the base. So you look at the, so you can have this shape. Right? It's a triangular prism. And area of that object is area of the base times the height of the object. Over here, area of the base is a square times the height, a times a, height is a, so a cubed. Over here, x times y for the base times z, which is the height. Over here, area of the base is a circle, pi r squared times the height of the cylinder. That's your can. Obviously, this one right here, right? There's the cylinder, right? Or the soda can. Right? So area of the base is the circle. You calculate the radius, pi r squared, and then times the height you can measure, so you have the volume of this. So we have these things, and that's the category. So if objects are anywhere in there, that's what the volume is. The next category I call spiky objects. We're going to talk about a cone and pyramids of all kinds. All right? So there is a spike at the top. Now the pyramid could be the 4-sided or the 8-sided, like those in Egypt. So you have this going on. They could be triangular, whatever. Spiky objects, it's always 1/3 pH. So now, what is the volume of the cone? See, if I asked this, 5 minutes ago, everyone would be like, what's the volume of the cone? 1/3 pi r squared h. Very good. See, you know it, like this. So learn categories. Don't learn one-by-one formulas. It's going to be way too many. All right? So you have the non-spiky and the spiky, and then the third option contains only one, the perfect one. The sphere, yes. It's a special object. So sphere gets its own category, and you are learning that formula by itself. So you have the this covers everything now, right? Covers everything. So I don't care whether your pyramid is 4-sided, 3-sided, 8-sided, 12-sided, as long as you can figure out the area of the bottom times the height of the pyramid times 1/3 gives you the volume of that shape. And this now creates everything in terms of the volumes. Surface area, well, you need to know area of the triangle, right? Area of the rectangle and square, and area of the circle, right? Those are the, there's a trapezoid, sure, IA plus B over 2 times the height. You can go all out on that one, right? You get that too. And that takes care of it. Now, done. So now we're going to take a look at the last problem for the engineering. We have a conveyor belt which is bringing in sand, and the sand is falling onto what is clearly going to be a conical pile. In time, that pile will grow, creating bigger cones. As the pile grows all the way up to conveyor belt, the pile of sand will start accumulating on the belt. Eventually it's going to become very heavy and it's going to break $1 million belt. It's a problem, right? All of that because the worker fell asleep, never shut it off. So what? We want to program this, automate it, so you are hired to create the code for it, right? Every problem is the same. If you're not coding, market does a good job. So we need to figure out a mechanism that will tell us, will tell the system, shut it off. Enough, right? Now, simple engineering will say, just put a photocell, man. When it reaches the height and the photocell is blocked, shut it off. No. Why no? Well, 2 reasons right off the bat, right? Or 3. A little spider kind of crawls in and blocks it. That's number 1. If you don't like spiders, then you might like birds, right? Or it's just dust. It's going to get dirty. You have to clean it constantly. You have to, right? So no photocells, right? Just compute it, right? It evolves with time. And this thing is going to have a radius and a height, and there's going to be a volume over here, and you know, the big one over here has the volume. It changes in time, right? And there is the change in height, and there is a change in radius, and change in volume, and change in surface area. Just get a formula, compute that, put that in a code, and let the computer shut it off. Or pay someone to look at it. And after 3 hours, yeah, done for the day. Let's do it. So what do we need for this problem? Incoming sand, gravel, corn, coal, whatever it is, garbage, right? So incoming rate, right? Incoming rate is going to be dV/dt, right? Because you are gaining volume in time by dumping something on a pile. So incoming sand or garbage or whatever it is, it's coming onto a pile, and that has to be the change in volume in time. You can put more, you can put less, right? It's determined by how much stuff is coming on the conveyor belt. So I hope that's clear. On the ground, you have your cone, and the cone over here will have change in radius in time, and it also have the change in height in time because, right? So now clearly we have the variables which we need to relate, right? The change in time, change of radius in time, change of height in time, change of volume in time. So it should be common sense at this point that we have to use the volume formula and hit it with the time derivative, right? Time derivative to come up with the related rates that will solve the problem. Great. The volume for the cone is 1/3 base times the height. And you guys told me that the area of the base is pi r squared, and then we have the height. Nice. That means that the formula we have to worry about is pi over 3 r squared h. And we need to hit that one with the time derivative, so derivative in respect to time, and that will give us the related rates formula that we need. What's this derivative? What is this derivative? Talk to me. Oh, you want to tell me the solution? Okay, I'll take that as well. What is this derivative? What do you see? Did anyone do homework for like 2-3 weeks? Holy nightmare. Yay! Product inside a chain. Hell yes. Radius is a variable which is changing. Height is the variable that is changing, and they're multiplied. You have a product rule there. Be very careful about those things. So pi over 3. Very good. Pi over 3. Copy the first one, derivative of the second, plus copy the second derivative of the first. That's your product rule right there. It's hard to see it. I'll put the red dot now. But there it is. So copy the first, r squared, the derivative of the second, derivative of h. Derivative of h is 1 times the chain rule, dh dt. Plus copy the second times the derivative of the first, which is r squared, derivative is 2r dr dt. And that's it. You know, you can walk away, but you really can't. It's way too many variables, right? Way too many variables. You have to calculate the radius, the change in height, the radius, the change in radius to get the change in volume. Generally, you don't have all of that. And this one over here, the volume is given because you know how much stuff is coming in. Right? I said garbage, corn, whatever it is coming in, sand, gravel, all of that stuff. So let's reduce amount of variables. You see, the cone which you are considering has a geometry, right? It has height over here, and it has a radius on the bottom, and that gives you on a side a right triangle. I'm going to draw this smaller, actually. Now, what is going to happen in time? In time, this is now green, so in time, the height is going to grow and the radius is going to grow, and it gives you a larger triangle. See that? So now what do we have? We have a proportion. We have a proportion. 2 snapshots in time. The old radius divided by the new radius is equal to the old height divided by the new height. See that? So I have this proportion that I can utilize to alleviate some of the variables. So let's say when you measured the, so example, radius equals 3, height equals 10, right? That's the state when you measured. So what happens with our formula? Without formula, we're going to have that r over 3 is the same as h over 10. Okay? And you can solve this. Say, for r, 3h over 10. Do you see that this would eliminate all r's? Right? When I replace this r and replace this r with this formula, what I get is all h's now. No r anymore. So I eliminated a variable with this thing here. But the only issue is now I still have the r dt. Well, that is also great because I can take the time derivative of this formula as well and come up with a relationship between these guys. The r dt is equal. If you ask me if this is going to be on a test, I'll hate you forever. I don't like that question. 3 over 10 dh dt. So now I can plug all of these. So this one and this one plug in. And the long formula I had before collapses because it loses variable r completely. Now you can solve this for age and then solve the other one for age, take the time derivative and kill ages. You can kill r's or ages, doesn't matter which way. I mean, the problem obviously will matter in the problem, but right now that we talk in general terms, could go either way. So what was my formula? dv dt was equal to pi over 3, open parenthesis, we are killing r by placing 3h over 10 squared dh dt plus, it was 2rh, so 2r is 3h over 10 times h, and then times the r dt, which is 3 over 10 dh dt. So I plugged everything in, replaced all r's. I replaced all r's. And now all I need to do is to just quickly simplify it. So pi over 3. What do I have over here? I have 9h squared over 100 dh dt plus 18h over 100 h squared over 100 dh dt. Wow, look at this. This is great. 9 and 18. Common denominator, common variables, h squared in both. We can just straight up add them. So dv dt is pi over 3, 27h squared over 100 dh dt. Cancel 3 and 27 to get your related rates formula of pi h squared over 100 dh dt. Why have I solved it this way? Remember what my goal is. To come up with a formula which will tell me the height and the change in height with the incoming amount of stuff so that I can shut it off when it reaches a certain height. This is how you design things. So when engineer tells you they don't do integrals and derivatives and use calculus, no, they don't.
Shouldn't it be 9?
Yeah, there's 9 there. There's a 9. You see the 9? It's right there.
I see it.
There's a 9 pi 8. Yeah.
Thank you.
You're welcome. Thank you. So we just developed the formula, and then you go off and you code this thing, and then have the right controllers connected to the right equipment, and the whole process becomes automated. Those are your jobs, guys. The automation, AI, medical field, medical research, teleportation, fusion, autonomous driving. And then there are 6 positions available in accounting. Anyone is interested. Some nurses, doctors. What else is there? Video game, obviously. Olympus is dying, I'm sorry. No amount of you two watching it will make it better. Yeah. That's the related rates. Just, get some rates and relate them. The vultures are back. They can smell calculus. You can smell how rotten everything is, right? All right. Exam is next class, so we have the review today and the lab time. So let's take a break and come back with refresh for more.